Today, we're going to talk about how we can train language models across different domains. Now, to do this, we're going to be using what is called the augmented SBERT training strategy, and we're going to be using the domain transfer flavor of that. So the training strategy is used where you have some data, but not enough. Or in our case with domain transfer, we have some data in one domain. So say maybe we have query question pairs, but we need Stack Overflow question pairs. And all we have on the Stack Overflow side are unlabeled question pairs. So what we're essentially doing is using that source data set, for example, query question pairs, to train a model that can then transfer its knowledge and label the Stack Overflow question pairs. Now, we don't need to stick with question pairs and question pairs. We can go from question pairs to semantic similarity pairs or anything else, but we do have to make sure that our source domain and target domain are at least similar. And we can think of this required similarity as a bridge across a gap between the source domain and target domain. The greater that gap, so the less overlap those two domains have, the greater this gap here is. And if this gap is bigger, we obviously need a bigger, stronger bridge. And we can think of that bridge as our model. We need a bigger, stronger model to bridge these longer or greater gaps between the two domains. So in this video, we're going to be going through one example, but I have tested these 5 different data sets. So what we can see here is the n-gram similarity. So this is how many n-grams overlap between the two data sets as a whole. So this is not a perfect measure of similarity, of course, because it's only capturing the syntactical overlap, and it's not really capturing whether the two data sets have the same language structure or are talking about the same topics that much. Although it does help, and this is just a very simple measure to help us figure out whether the two domains that we're trying to transfer across will be easy to bridge or not. So we would expect from this that the medical question pairs down here, because of these low similarity scores, it would probably not be the best domain transfer to these different domains. Whereas these different domains, STSB, RTE, MRPC, and query question pairs, are all reasonably similar, so we'd expect the performance or the transfer or ease of transfer between those domains to be much smoother. But like I said, this isn't perfect, and in fact, one of the best domain transfer performances that I saw was from the medical question pairs to the query question pairs, which obviously makes sense semantically because question pairs will probably have more of a similar structure than entailment pairs, which is what we have up here with RTE, or just semantic textual similarity pairs as we have up here. So that does make sense logically, but it's not really reflected in this chart here. So this is the overall strategy that we're going to follow with domain transfer augmented SBERT. So the first step is to get our data. So we're going to have a labeled source data set, which in the earlier example would have been the query question pairs. And we're also going to have the unlabeled target data set, which would be our Stack Overflow question pairs. We're not actually going to use those 2 examples. We're going to use, from here, we're going to go with MRPC as our source data set and STSB as our target data set. So we'll go ahead and we'll get our labeled source data. So that's going to be MRPC, and we'll train a cross-encoder model with it. Now, the reason I've just quickly mention is the reason we're training a cross-encoder model rather than a bi-encoder model, which is a sentence transformer, is because we need less data to train a good cross-encoder. And the cross-encoder here is only used to label the target data. So we need less data to train a good cross-encoder, but cross-encoders are also slow, which is why we don't use a cross-encoder over here as our final model. So we're basically using that greater performance with less data to build a data set over here that can train a fast sentence transformer over here to a similar level or similar performance to that cross-encoder. That's basically what we're doing. It's knowledge distillation from our cross-encoder all the way over to our sentence transformer. That's all we're doing. So let's jump over to code and we'll have a look at how we do those or perform those first two steps. Okay, so we're starting with the source domain, MRPC, as I said, and the target domain is STSB. So first thing we do is get that source data. So we use Hugging Face datasets for this. So you may need to pip install that. So just pip install datasets. And from datasets, we import load datasets. So this is just going to load the MRPC dataset from Hugging Face, which is stored in the larger glue dataset. And MRPC is like a subset of that. And then we're taking the train split from there. And we can see the dataset features here. So we have sentence 1 and 2, which are sentence pairs that we're going to be learning from in order to label the other STSB sentence pairs. And we also have the label as well. And we only have 3.6 thousand samples here, which is quite a small number, particularly for a sentence transformer. So that's why we're going with the cross-encoder here, so that we can build something that has good performance, whereas a sentence transformer might need a little more data, although not necessarily. So we need to first format that data for training, and to do that, we just go through each row in the dataset that we just downloaded, and sentence transformers always uses this input example object. So all we're doing here is creating an empty list, and then within that empty list, we're populating it with these input examples, which contain sentence pairs here, and also a label. And then behind the scenes, we're using PyTorch. So we also need to initialize a PyTorch data loader with those input examples. And we're using batch size 16 and also shuffling that data as well. So that's our data's ready for training the cross-encoder. And then we move on to, if we'd like to, we can move on to adding this validation set as well, which is useful because then we get a performance from our source validation set. If possible, you really probably want to switch this out for the target dataset validation set. So this would be, in our case, it would be STSB. I'm not going to do that here, just to emulate in like an actual project. You may not have this validation data from your target domain, but I would definitely recommend, if you do have the time, to just manually label something so that you can check that performance, because you will want to do that later anyway. But for now, we'll just use source dataset. We're using this cross-encoder because we're training a cross-encoder, and it's coming from this cross-encoder section of sentence transformers library, and it's a correlation evaluator. Okay, so that's going to check the correlation between the labels that we have here, so the true labels in our validation set, and the predicted labels from the cross-encoder, because the cross-encoder does not output sentence vectors like a sentence transformer, it outputs a similarity score. And then we just initialize that correlation evaluator we're using from input examples. So we're using input examples up here, so we use that method there. And yeah, that's our training and validation data ready to go. So we can go ahead and start training the cross-encoder. So for training Cross-Encoder, we load this Cross-Encoder object from sentence transformers again, just using a BERT-based case. So that's the sort of initial model that we're using to initialize our Cross-Encoder from. So that's coming from the Hugging Face models hub. And the number of labels. So this, you can change this if you are training a Cross-Encoder that you like to predict NLI labels, for example. So you'd have 0, 1, 2, which would be your contradiction, neutral, and entailment classes. You would put something like 3 because you have 3 labels there and you want to output 3 labels. But for us, we want to output a similarity score, so we just have 1 label. Then we have here, we have number of epochs. Now, anything more than 1, you're probably going to overfit. So I think always stick with 1, unless you really have reason to do otherwise. And here we have the percentage of warm-up steps that we're going to use. So this is the number of steps where we're not going to be training at the full learning rate, but we're going to be gradually increasing up to that full learning rate. So it's quite high, 35%, but it's what tends to work best. I find with cross-encoders, a higher percentage of warm-up steps tends to work reasonably well. And then over here we have our optimizer parameters, which is another training parameter that I've modified a little bit. So here we're using slightly higher than the default of 2e to the minus 5. We're using 5e to the minus 5. Now, everything else is as you usually would with the cross-encoder. So we're using the fit method. We will do that with a sentence transformer as well. The train data loader, this is slightly different to the sentence transformer parameter, but otherwise everything is exactly the same way. So we're passing in our source data, which is the training data loader that we created earlier. We have our evaluator, number of epochs, warm-up steps, learning rate, and where we are going to save the model. So BERT source is going to be MRPC Cross-Encoder. So that trains our model. It doesn't take long. You can see here it took on this computer 14 seconds. It's very quick. And then we can go ahead and label the target data. So that's onto the next step. So let me actually go back to here. So we can kind of cross these off. So we've labeled the source data and we've trained our cross-encoder. Okay, so this is our performance of the cross-encoder models. So that is the source models over here on different target data sets over here. So the source model for MRPC on the STSB target data over here. So this is the validation set of the STSB target data is what we are aiming for. So this 0.63. Now we should be able to get better performance in this, I think, but we'll have a look. And we can also see, I said the STSB is quite easy as a data set to get good results on. And we can see that here because all of these do achieve better performance. But what I really want to focus on here is the BERT based on case performance as a benchmark, because this is what you would get if you didn't have your any training data, or which we don't have any target domain training data. Instead, we're kind of using this AugSBERT training strategy to train from the source data set. So these are our benchmarks, and we can see that from here, so we have these red circles which represent that the model performance has decreased from that benchmark, and then the blue ones over here, they represent that the model performance has increased from the benchmark. And then we also have gray, which is to indicate that it was the same value or maybe a couple of points higher, but not that much higher. So we can see straight away that the worse, and we can see that it does perform worse. So all of these glue data sets don't really correlate so much with the medical question pairs, and we can see a lot more red in this column. So that is to be expected. In the other glue datasets, we see a lot more grey and blue. So the results are either similar or better. So obviously the next bit is this target domain part. We're not going to be doing this optional augment data because it doesn't tend to, at least for these data sets, I didn't find this to help much. But if you do want to see how to do that, the last video that we did on augmented SBERT, and last article, does cover that augmentation of data using something called random sampling. So we're just taking random samples from our data set and creating new pairs with that and then labeling them with our cross-encoder. That's all there is to it. So, but for this, I didn't find any significant performance increase. It did increase the performance for a couple of the models a little bit, but not a huge amount. So I think for the time it takes, it's probably not worth covering in some cases. But if you think it might help, especially if you have a small data set, I would check out the other video and article. So we need to get our unlabeled target data, and then we're going to skip that step. So we'll just cross it out. And we are going to label it with our cross-encoder. So from up here, we're going to take that and label this target data. So let's have a look at how we do that. So yeah, the labeling that target data, first we need target data. It's same again, we're just going to download that from the Hugging Face datasets library. So we're coming from the glue, like larger dataset again, but this time we're using STSB, which is quite an easy dataset to get good results on, to be honest. So I wouldn't expect this sort of performance for everything, but this is just the example we're going to use here. And so we're obviously using the training split as well. And we can see here, okay, in that dataset we have the features, sentence 1, sentence 2, and we also have the label. So obviously we don't actually need to use the cross-encoder to create our labels, but we are going to, because that's the whole point of this training strategy. And I just couldn't find a reasonably good dataset that didn't have the labels already. So we're just pretending they don't exist. So this here, it's not there. If you're struggling to train the cross-encoder, or you can just download it from here, by the way, or if it's taking a long time. I mean, it shouldn't take that long, but I know on some machines it can take a while. So just if you're following along with this in real time, I would do that if you're having any issues. So we have our target data, and what we do is we zip those sentence 1 and sentence 2 together. So I'll delete that. Let's say we have sentence 1 and we have the first, I don't know what it could be. It could be, I think it's something like a plane. A plane is taking off. And we would have basically a tuple where we have the first sentence, and we also have the second related sentence, which is something like an airplane lands. I don't think it's lands, it is something to taking off as well, but I don't remember what exactly it is. So you would get something like this, and then the next one would be something else, like the dog runs, and I don't know, the dog walks. Okay, so something like that. So we're getting these like tuples of sentence pairs, and we're feeding them into the predict method of our cross-encoder, and that will return a set of scores. Obviously, these here would be reasonably high similarity because they're talking about a similar topic, not necessarily the same. We've got walks and runs and lands and taking off, but they would be still reasonably high. And then what I'm going to do, so this just makes things easier in terms of seeing what we're actually working with, what we're looking at. So I'm just going to pass those sentence 1s and the sentence 2s and then those new scores into a pandas data frame. And then we can see everything here. So we can see a plane is taking off and an airplane is taking off. So that was the first two I was talking about. And then we have all the labels that our cross-encoder is predicted. Now, all of these are pretty high because these are all very similar, semantically similar pairs. So that's what we would expect. But later on, there are other pairs which are less similar. And then we move on to training the Bi-encoder. So let's quickly switch back to our visual again. Okay, so now we have identified, or we've downloaded our unlabeled target data. So cross that off, and we've also labeled it using our cross-encoder model. So the final step, as we saw, is training our Bi-encoder with that labeled target data. So let's have a look at how we would do that. So we have our labeled target data in this pandas data frame here. So we're just going to iterate through the rows in our data frame, and I'm going to append all those as input examples as we did before to this data list here. Okay, and we have our sentence pairs and we have the predicted labels in there. So once we've created that list of input examples, again, we're just pushing all of that to a PyTorch data loader. And from there, we can go on and initialize our sentence transformer. So to do that, we are using models and sentence transformer from the sentence transformers library. And so the sentence transformer takes the typical transformer like BERT, and what BERT outputs is 512 word vectors. And what we want is one single sentence vector from our sentence transformer. So to do that, we need a way of translating those 512 word vectors into a single vector. And we do that by pooling all of those 512 tokens into one token by taking the average value across each dimension. And that's all we do there. So that's why we have this BERT layer followed by a pooling layer, which is taking the mean pooling. And then we combine both of those into a single sentence transformer object. And that's our sentence transformer initialized, but obviously we need to train it. So we come down here. To train it on the data we have at the moment, we have continuous values in our labels from 0 to 1. So what we can use is the cosine similarity loss. So we initialize that. And then again, we don't want to overfit. So epochs is set to 1. And this time we're using a lower number of warm-up steps, which is 10% this time. And we train with that. So once that is done, we are completely ready to train, and we just call model fit. So train objectives is slightly different to what we saw with the cross-encoder fit method, but everything else is the same. We're just using the default value here, so 2e to minus 5. So you don't really need, you can remove that if you want, but if you do want to change that, I put that in so you can see where you would change that. And yeah, we're ready to train. We go ahead and train and see how that performs. So we evaluate it. This time we're not using cross-encoder, so the evaluator is slightly different. This time we're using an embedding similarity evaluator, which is going to take two sentence vectors, and it's going to calculate the similarity between them. And then it's going to compare that to that predicted similarity to the true similarity as per our validation set here. So in that validation set, we do have these labels, but in STSB, those labels are in the range 0 to 5. So we use this lambda function to divide everything by 5, which brings us into a range of 0 to 1, which is what we need for this embedding similarity evaluator. And then, as we did before, we're creating that list of input examples. And then we can initialize the evaluator. So we're using the embedding similarity evaluator from input examples again, because we have input examples, and we're passing in our input examples data. And write CSV is false. That just means I will print the score to our notebook. And then to actually evaluate, all we do is pass the model to our evaluator, and it will do everything for us. And we get a similarity here, or a correlation score of 0.76, which is pretty good. You can think of something like 0.5 is kind of like your moderate correlation, and 0.8 is like high correlation. So that's pretty good. Okay, and for the final quick part, I just want to have a look at the other performances that I found, because not everything is going to be as good as that, what we just got there. So we can see, so this is what we just did over here. We got 76 just now, so we got slightly higher than what I got before. So we got 76 here. But obviously, like I said, STSB is an easy data set to get good results on, and the others are more difficult. So the rest of them are, you're more in this sort of moderate similarity range or correlation range. So the medical question pairs data set actually performed better with the Bi-encoder training than it did Cross-Encoder training, but nonetheless, they're still within the same sort of range that I would expect. It's not a massive improvement. This is the benchmark down here, and there are a few percentage points better, which is probably reasonable, particularly because they were not, these glue data sets were not that similar to our medical question pairs data set. So that makes sense. And then the other ones, yeah, they're all sort of within that moderate range. The one that I suppose did surprise me, although it does make sense, I mean, the question pairs is this one here. So the transfer from medical question pairs to Quora question pairs was pretty good. And I suppose if you have a look at here, from Quora question pairs to medical question pairs, it's not as good. And maybe because the language in Quora question pairs is simpler than the medical question pairs, I'm not sure. But from medical question pairs to Quora question pairs, it worked quite well. So that, I suppose, points out where that n-gram similarity doesn't always correlate exactly to what you would expect. But anyway, I think the results from this are probably pretty typical from what you can expect. Now, I think this can be really useful if you really don't have any labeled data within your target domain, to at least squeeze out a few percentage points of performance more than you would be able to without this training strategy. So for that reason, I think this can be quite useful. Whether or not it is the best approach to take will depend on your data. So I think it's useful. Not always the best option, but definitely something useful to know about and be able to apply if needed. So yeah, that's it. Thank you very much for watching. I hope it's been useful, and I will see you again in the next one.